Well, this is our third lecture in Chapter 12. I wish I could devote more time to it. It's really a lot of information in Chapter 12, but it really sets us up for Chapter 13. And Chapter 13 is, now that you have a lot of the understanding of the principles of thermal radiation, properties, processes, and the details, now let's make some simplifying assumptions and solve some engineering problems in the next chapter. All right. So we covered a lot of material. Let's continue on. Last time we talked about this equation. This equation is Planck's distribution. It shows that the spectral emissive power or flux of a black body is related to the wavelength of the emission as well as the temperature of the surface. And when you plot it, you get these very unique curves showing you very low spectral emissive power for low temperature surfaces. Here's a 300 Kelvin, that's a nice one, around room temperature. And we find a lot of emission goes between 2 and 40 microns. And then as the temperature goes up and up, you can start to bleed in and get significant emission in the visible spectrum. And then the approximation to the surface of the sun, 5800 Kelvin, and you get a lot of emission, very intense, but it's at the surface of the sun. There's a lot of spreading of the photons by the time it gets to the surface of the Earth, but it's still intense when it gets to the surface of the Earth, isn't it? The intensity of light. All right. So it's a function of both wavelength and temperature. How did we go from the Planck's distribution to the Stefan-Boltzmann law? We integrated. So you just integrate E lambda B with respect to lambda. I can't write lambda. I can try it again. Lambda from 0 to infinity, and that gives you E sub B. And so it's very strongly a function of temperature, and you must put absolute temperature into the Stefan-Boltzmann law. We know it's a function of wavelength. Sometimes we're interested in what is the fraction of the emission that's in this band of wavelength. So the way they've set that up is they've integrated from 0 wavelength out to a particular wavelength of interest. The fraction that's in between 0 and lambda is tabulated, but it's tabulated in a unique way. It's tabulated as a function of the product of the lambda of interest and the temperature of the surface. It's kind of unique that you can compute this as just one component, one integrand on this integral, but that fraction is simply a function of the product lambda t, the wavelength of interest and the temperature of the surface. You can see that it starts at 0 and then it goes in larger and larger. Here it's around 25%. This is a Wien's displacement law. That's the maximum for that given temperature. But then there's a lot with 75% will be at longer wavelength than at the maximum. This table is continued, and it just goes on. Let's solve the problem. A surface temperature of the sun is approximately 5800 Kelvin. Determine the fraction of thermal radiation emitted by the sun in the spectrum with the visible spectrum, which is 0.4 to 0.7 microns. How much of that energy of emission from the temperature of the sun is what our eyes can see? And how would we make the calculation? Well, we would compute lambda times T when you put in 0.4 microns times 5800 Kelvin. And we'd find that, look it up somewhere in the table, read off that fraction, and that would give us the fraction from 0 up to 0.4 microns. Then we would go lambda times T where you're doing the other end, 0.7 times 5800 Kelvin. Whatever that number is in micron Kelvin, look down, get that other fraction, take the difference of the two, and that's what lies in the visible spectrum. So here's the calculation. So 0.4 to 5800 is 2320. So we look for 2320 somewhere in this vicinity right in here, 2320. Do interpolation between 10 and 14%, find 12.5%. How much energy from the sun is in the UV region? 12.5%. All right. Then we go from 0.7, it's up to 49%. So from 0 up to 0.7 microns, 49, you subtract off the 12, and that leaves you 36.7% is in the visible region. What's in the infrared region, greater than 0.7? How much? Almost 50. Well, it's actually going to be 1 minus 0.491, isn't it? Yeah. So it'll be 50. Won't it be 50.9? Right? Yeah. All right. So the table's slick, but you have to go and interpolate, unfortunately, in it, or code it up some way. Now, I showed you roughly how to get a good grip on what is the wavelength of emission if the surface is 300 Kelvin, right? So here's the 300 Kelvin. Come on now. There's 300 Kelvin, drop down from the peak, about an order of magnitude. Looks like it's between 4 and 40. Put it out here, 40, right? So what is the fraction between 4 and 40? Now we have the tools to make that calculation. So we take the 4 times 300 temperature, 1200 micron Kelvin. Look at the fraction. It's 0.2%. Very little. Then 40 times 300, 12,000 micron Kelvin, 94.5%. Hence, the fraction between the two is 94.5%. Almost all of it. I mean, there's still 5% or more out. Where is it typically? It's out in the longer wavelength IR region. How about for 1,000? So I mentioned this 1,000. Go from the top down an order of magnitude. From here, which is a little over 1, I forget what I did. Did I do 1 or 2? I did 1 lambda. So 1 micron. Out to, right out the other one is a little over 10. So I picked 12 microns. And so 1,000 Kelvin is between 1 and, I think I messed that up, 12 microns. Typo, right? So it's 95%. And then at 5,800 Kelvin, where's most of the energy? We already know that 37% was in the visible spectrum. You include a little bit of the UV and a little bit of the IR, plus all of the visible. 95% falls between 0.2 micron, right? 0.2 micron, right there, and 2 microns, right there. So that covers about 94%, right at 94, 95%. All right. Let's talk a little bit more about emissivity. This is how well the real surface emits. Well, you have a fraction. Emissivity is simply a fraction of the emission compared to the emission if it was black at the same temperature. So how many watts per meter squared, or just watts for a given fixed area, compared to watts per meter squared if it was a black surface? Black surface, the best emitter. Okay. You can take a look at as a function of wavelength. So you could talk about the emissivity at a particular wavelength. And at that wavelength, let's just pick one. Let's pick this wavelength right here. On this plot, there would be the actual actual emission at that wavelength from a particular surface compared to the black body, and that ratio would give us the emissivity. So it would be E sub lambda actual divided by E sub lambda black. It'll be less than 1. It'll never be, the emissivity will never be greater than 1. And you can tell the emissivity for this problem varies as a function of the wavelength. You just see that ratio of those two segments. Okay. And so what are we showing over here? So this is the spectral characteristics of the emissivity as a function of wavelength. What is shown on this half? It's the angular, the directional. So the spectral and then the directional characteristics of the emissivity. What are they showing on this side, the left side, right here, by having this constant arc? It's the I, the intensity of at a particular wavelength. That's not as important right now. Lambda, they already covered that. But it's a function of theta, isn't it? What's theta? That polar angle. So they're showing you the directional characteristic. And over here they're saying not just a black, but they're showing a real surface. What's the difference in the length of the line going from here out to there versus here out to there? That ratio is the emissivity. I wish they would have maybe started this arc and stayed on the same side. Because if they would have shown it like this, that ratio would have been the same ratio regardless of theta, wouldn't it? And then you would talk about the emissivity as a function of wavelength, as a function of the polar angle, and here it would be the ratio of those two. That would be the emission at that wavelength in that direction, the emission wavelength black body in that direction, which would be cosine. But if it would have been the same length, then that would have been a constant. Maybe it would have been, if I'm just looking at this illustration, maybe it would have been 70% is the ratio. But what do they show over here for a real surface? It starts, looks like it's staying out there, but what's happening? So for large polar angle, the emissivity is getting smaller, isn't it? Isn't the emissivity getting smaller? One of the things they'll do is they'll look at theta equal to 0. That's the normal direction. It's perpendicular to the surface. And they'll make one measurement for a particular surface, and then they'll report that. And if it has no directional property to it, then you would just use it for all directions. So here they're showing you the normal emissivity. Again, sometimes like, what's normal about this? Well, it's the direction. Okay, theta is equal to 0. And let's take a look at a few things. Special paints, anodized finishes, very high. It's up close to 1, maybe 0.9 to 0.98 or something like that is the range. How about for your skin or water or vegetation and leaves and things like that? Very high emissivity. How about for minerals and glasses and carbon and graphites and ceramics and oxides? But they blow up this lower portion between 0 and 0.15 and they expand it. What has some of the lowest emissivity values? Polished metals, foils, films. Where do you see any of that? Mirrors, yeah. You could just get a foil that you use in the kitchen, right? The aluminum foil. That would have a very low emissivity. So what's the difference between polished metals, metals as received, or unpolished metals or oxidized metals? Notice they start to get a large range depending on what sort of oxidation has occurred and what type of condition of the surface of the metal. Yeah, it's going to higher and higher emissivity. All right. What does the word incandescent mean? It's so hot that it's giving photons off in the visible spectrum, and so I can see it. things are always giving off photons, but they don't have enough intensity in the visible spectrum to see. But if they get hot enough, then you can see it, like white hot, red hot. All right. Well, there's a characteristic about especially the large polar angle associated with different metals. Let's say if a metal is electric conductor. What happens is you'll have, first of all, for electric conductor, if you look at it, it's a metal. It was a lot lower emissivity to begin with. The normal emissivity is lower than maybe a non-conducting solid like a ceramic. So we'll start this illustration and we'll do a low value for the normal emissivity. If starting at this point right here, can you just visually tell me what is the value of the emissivity, the normal emissivity? What do you read? How much? 0.2? Yeah, 0.2, 1/5. The length of this line is about 1/5 to up here. Okay, so if it stayed and it wasn't a function of the polar angle, it would just stay at that radius. But if you have an electrical conducting material, sometimes when it comes out like this, what's happening to the emissivity at shallow angles? It's getting larger. It's larger. So if you have a metal sphere and you heat it up so it's just high enough temperature that it actually glows. Clicker question here. You will be able to see it, but will you see it where it's brighter in the interior of the sphere? Or will it be brighter, glowing more strongly along the edge of the sphere? I have a sphere. It's metal. It's electrically conducting metal. I heat it up such that it glows. In the room, there's no other light. So if I turned off all the lights, all I would see is the glowing sphere. Where would it be more intense? The light coming from it would be in the center or the edge? Well, what you'll have is you'll have a glow more strongly on the edge. In the edge material, you can see more clearly. All right? Because it's much stronger at that shallower angles that you're seeing. And so what you're seeing directly in the middle is what's coming normal off of that surface. All right. So let's go ahead and grade this. And what's the opposite of that? Well, if I have a sphere and the sphere is a non-conducting, this one was conducting, then a non-conducting, maybe it has a blue right here, but then when it comes, it tucks in. So what happens to the emissivity at large theta for non-conducting? Just the opposite. It's weaker. So it'll have a stronger incandescent radiation in the middle of the sphere. All right. Well, there's three things. Now that we talked about emission, let's talk about the incoming radiation. What can happen with the incoming radiation? Well, it can either be absorbed on the surface, transmitted through the surface deeper into the material, or maybe through the material if it's a thick slab, or reflected. Those are the three things. There's not four things that can happen to it. So it's either absorbed, transmitted, or reflected. Well, you take the ratio of what's absorbed over all of the incoming, the incident irradiation, and that gives you the property absorptivity. For the absorptivity is a property that ranges between 0 and 1. When would it be 1? Well, it's a perfect absorber. Everything that impinges on it will be absorbed. Have we been introduced to a surface like that? Yes, it's a black surface. It's a perfect absorber. The black body is a perfect absorber as well as a perfect emitter. So in that case, and only that case, the absorptivity is 1. Transmissivity, well, that's the ratio of what is transmitted over everything that's coming in. If it's opaque, well, what was opaque? I know this is not a vocabulary class, but opaque surface means can't see through it. Right. If you can't see through it, what is the transmissivity? 0. And so then we know that either it's absorbed or it's reflected, and that's the only thing that can happen to it, so that they sum up. Those two, the absorptivity and the reflectivity, add up to 100%. Well, what's the reflectivity? Well, the amount that's reflected divided by all. All right. So in all surfaces, not just opaque, the sum of these three is equal to 100%. So we have these three properties: absorptivity, transmissivity, and reflectivity. Now we get into something that's really tricky. There's a lot that could be spent on Kirchhoff's law. Let me just set it up and then talk about it. Think of two large black infinite plates. So we have two large black plates. All right. So if I have the surface right here, and it's going to be emitting some photons, I'll try and draw it as a cosine distributed emission, right? Where do 100% of the photons that come off of surface 1, where do they eventually go? They're going to hit surface 2. That's the only place they're going to go. They're not going to go back to 1. And if both of these plates are black, then I know it's a perfectly cosine distributed emission from 1, and I know that everything that hits on 2 is absorbed. True? True. Then if I have the temperature at 1 is uniform and the temperature at 2 is uniform, right? Then what happens if the T1 is equal to T2? What can you conclude? Would there be a net transfer from 1 to 2? That has to be 0. Has to be 0. What would be a good equation for Q net? We know it has to be 0, but what would be a good equation? Well, everything that comes off of 1, but it's emitting as a black body. That's the total emission over all wavelengths, over all angles. And then what about the balance? By itself it can't be, so it's emission minus the incoming, which is absorbed. And so you get this funny G sub 1. But what is G sub 1? Isn't that EB1? EB2. Isn't what comes off of 2 equal to the incident on 1? So what you have is you have EB1 minus EB2 is equal to Q net. When T1 is equal to T2, we know Q net has to be 0, and we know then EB1 is equal to EB2. But one of the biggest conclusions is, right here, is that the incoming on surface 1 is EB2 when both surfaces are black. Now, the outgoing EB1 is cosine distributed. If I wanted to take into account the angle of the incident, G, would G be cosine distributed? Is G cosine, I can't spell cosine, distributed? Meaning that you're just the opposite. Instead of going out like this, shown like that, they would be coming in. So fewer would be coming in at a shallow angle, and a lot would be coming in at the normal angle. G. I shouldn't have tried to change the shape. Let me give you more time. A is true, which is yes. B is no. So is G cosine distributed? Yes, A, no, B. And I'm trying to draw it with the same shape as, so here is G1. All right, let's see how we did. Split. Well, it is cosine distributed as well. It's probably not trivial to prove, but think about this. You have a lot of little chunks right here that are shooting toward this surface right here as like a little point, a little dA. To shoot from here to there and hit it, I've got to come off at an angle theta 2. True? And that's equal to theta 1, the incident, incoming. Does that make sense? If can somehow this little chunk of dA2 send photons it's going to come off at theta 2 and be incident at theta 2, the same angle. And so everywhere along here it's cosine distributed emission. It's going to be cosine distributed irradiation, G, on the surface 1. Did that help? Well, now I'm going to build up, because Kirchhoff's law now considers something about this being not black. 1 is now not black. All right. Well, I thought I would just show it to you. Here it is. Same thing. What are we going to do with surface 2? Leave it black. But let surface 1 have an emissivity. All right. So if surface 1 has an emissivity, you can talk about the spectral directional characteristic of the emissivity, or just average over all wavelengths and all angles. That's the easiest introduction. The next slide will consider wavelengths, and then you could do another slide for all angles. But so if I have just talking about one emissivity averaged over all wavelengths and all angles for surface 1, then I can have an energy balance Q net, which is how well it's emitted from surface 1. Doesn't that look reasonable? Emissivity 1, EB1. That's how it's going out. And then this is the incoming G1, but some of it's absorbed, not all of it, only alpha 1. And now, should I have alpha 1 here, the absorptivity of surface 1, or should I have alpha 2 here? Do you see my question on alpha? I have emissivity 1 here, but do I have, should it be alpha 1? Yeah, because it's what happens when it hits surface 1. Is it absorbed? That's the absorptivity of surface 1. Okay. What are we doing from here to here? G1 to EB2. Surface 2 is a black body. The only thing coming off of surface 2 is emission from surface 2, and that's the only thing incident on surface 1. So we can replace G1 is equal to EB1. All right, so now if T1 is equal to T2, isn't that EB1 equal to EB2? So now these two are the same if T1 is equal to T2. We can combine Q net. So Q net is equal to the emissivity 1 minus absorptivity 1 times EB1 or 2. They're the same. And if T1 is equal to T2, not only is EB1 equal to EB2, but also Q net's equal to 0. So if Q net's equal to 0, either this product, part of the product is equal to 0, or that's equal to 0. We know EB1 is not equal to 0, so what do we conclude? And that's the big conclusion of Kirchhoff's law, that the absorptivity is equal to the emissivity. But there's a number of little restrictions in this, and I'll get to it. But first, let's expand it by relaxing and saying at each wavelength, do the same thing now. See, we started, then we did two blacks, now we do one gray with the emissivity and the other surface black. Here you have it where I'm interested in the surface 1 has emissivity, but it's the spectral emissivity of surface 1. And it's not uniform. It varies as a function of wavelength. All right? Well, what you would do is say, I'm going to calculate Q net for each wavelength and then do the integral integrating over all the wavelengths. Do you see that equation? I don't want to get bogged down in it, but does that make sense? What do we do from here to here? Surface 2 is black, hence the G1 is equal to EB2, and we're interested in as a function of wavelength. We assume that consider the case T1 equal to T2, then the black body, the spectral black body emission from 1 is equal to the black body spectral emission from 2, and Q net's equal to 0. You combine this, you see that the integral, this component times that over all wavelengths is equal to 0. The only way that occurs, think about this, the only way it occurs is that each and every wavelength E lambda I or E lambda 1 is equal to alpha lambda 1. I didn't include another slide, but you could do it not only as each wavelength, but at each orientation of the surface, each theta. If you did it, you would get to the very general result, which is really Kirchhoff's law, saying the emissivity of a surface at a particular wavelength, at a particular incident angle, at a particular temperature is equal to the absorptivity at that surface at that wavelength, orientation, and temperature. But how do we often use this result? We often use it like I showed before. We just say, okay, emissivity averaged over all of the angles and over to all the wavelengths is equal to the absorptivity. When does that not work? When does the emissivity not equal to the absorptivity? Well, take the case of two plates. Let's call this one the hot plate and this one the cold plate. And the temperature 1 is much, much greater than temperature 2. So this is T2 over here. Talk about the emission of from surface 1. What would it be like? Wouldn't it be at short wavelengths? It's a function of lambda. Wouldn't there be a lot of emission at short wavelengths? What about the emission from the cooler surface 2? I know that I'm grossly exaggerating. There's a great height difference as well as a shift. So you need to put this on a log scale over here for the black body. Okay, well, that's the emission from each of those surfaces. What about the irradiation, especially for surface 1? The irradiation from surface 1 is the emission from 2, isn't it? All right. Let's take a look and say, what happens if I have the emissivity of this surface and it's very, very low at short wavelengths? Somehow it goes up and is very high at long wavelengths. What's going to happen to that exchange between the two? Instead of having uniform emissivity at all wavelengths, I have it low emissivity at short wavelengths. Well, this surface is hot. Is it going to be throwing out as many photons as if it had been flat all the way across? The emission is going to be lower at that hot surface because it's trying to emit short wavelengths, and it has a low emissivity, doesn't it? All right. And then the incoming will be based on surface 2 temperature, and it will be gobbling them up. It'll be absorbing them. So when you have dramatically different temperatures and you have a variation in the spectral emissivity, and also the spectral absorptivity truly is the same, because it is, Kirchhoff's law gives us that the emissivity at that wavelength is equal to the absorptivity at that wavelength. Then you've got to be careful, because if you jump from here, which is true, to here, that is regardless of the wavelengths, but the wavelength for the emission is short, and the wavelength for absorption is long. And so it's not true in that case for the average value. Actually, engineers exploit this. You probably have seen something like that. You want a good solar collector. What about the photons? We'll talk about the wavelength of the photons from the sun coming in, short wavelength. Make a material that grabs them, absorbs them. But now that you've gotten it hot, it wants to send out its own photons. True? But it's not going to be sending them out at 5,800 Kelvin. It's going to be sending them out at 300, 500 Kelvin. I don't know what the temperature your collector is, but it's going to be sending them out, right? You would like it not to send them out very well in those longer wavelengths. So absorb very well in the, 0.2 to 2 micron, but don't send them out in the 4 to 40 micron. So you would just want the opposite. You would want a high absorptivity, drop it, low absorptivity, which means a high emissivity, drop it, low emissivity. Such that if your solar collector would gobble up all of those short photons, short wavelength photons from the sun, but not emit. Let's spend just 5 minutes on solar radiation. A couple things are going to impact you in your career. One of them is climate change. As engineers, you're going to be tasked from the government, from companies, to do something about the climate change. And this is the part of the curriculum where probably you get some exposure to it. And it's all on energy and heat and temperature. True? So what happens is we have coming in from the black body, we have a real solar irradiation. It's slightly different than a pure Planck's distribution. Why? Because things are happening on the surface of the sun and the fusion, and so they're spitting out photons in preference. But it's pretty well fitted to this 5,800 Kelvin Planck's distribution. There's a few little bumps. This extraterrestrial, what does that mean? At the outer surface of the Earth's atmosphere. That's what's coming in and starting to interact. What's between the surface of the sun and the Earth's outer atmosphere? Pretty much vacuum. Just space, empty space. So it's not being absorbed or reflected much in there. What happens here, though, is that it goes through the Earth's surface, and now it finally gets from the atmosphere down to the Earth's surface, and this is what's bombarding you and your skin, your surface of the plants and vegetation, etc. And what is dramatically affecting the extraterrestrial to the Earth's surface? The presence of O3. The name of O3 is ozone. Yep, very high. Ozone. So ozone knocks out a lot of UV. And that was the great scare. We were putting out man-made products that were depleting the ozone, and we're going to be getting more skin cancer, etc. What else? Water. If you have a very cloudy day, there's a lot of water vapor up there, well, it's going to knock it down more. But it'll knock it down in particular wavelengths. All right. But you're doing energy balance, short wavelengths to incoming, the solar irradiation. You averaged over all of the time and all of the space of the surface of the sun. I'm sorry. Here's a number to remember. I need to go back and read this slide. At the Earth's outer edge of the atmosphere, there's about almost 1,400 watts per meter squared right there, directly. But the Earth's rotating, isn't it? Okay, some of the Earth's surface is in the dark. Some of it's on the polar end caps. It's not as intense as it shifts from summer to winter as well. So you average over the time and the surface of the Earth, and there's about a constant average 342 watts per meter squared way up there, hitting on the outer atmosphere. What happens when it comes in? Well, a number of things happen. A lot of it gets back out. And comes and absorbed, and then you have surface emission, and then that goes out, cloud emissions, outgo. But you have to have a net balance. Otherwise, what's going to happen? You're going to bake the Earth. Isn't that the concern of melting ice caps? And so somehow, man-made emissions have changed the characteristics of the long wavelength rejection of heat from the surface of the Earth, and you'd have a net buildup. So that's what the CO2 is doing. So what happens is you have to remember a lot of the Earth's surface around 300 Kelvin, it's trying to radiate. There's a lot of it in the energy balance. And if it can't get out because of absorption due to CO2, then it's trapped in, and you have climate change. Well, that's what I wanted to cover. This is a very long chapter. Thank you for your attention. I'm done. Thanks.